The ImPACT Tough Robotics Challenge program is developing robotic technologies that work in extreme environments, such as sites affected by disasters. Current robot systems are fragile and don't work unless conditions are perfect. This project aims to raise the toughness of technologies, thereby removing constraints in disaster situations. Field evaluations are a vital part of the project. We are developing robots useful on-site, using test data from simulated disaster conditions. On the basis of investigating actual disaster sites, such as the Kumamoto earthquake, scenes of concrete rubble piles and the interiors of collapsed houses were recreated. For plant disaster prevention, to improve the efficiency of robot inspections and increase safety, industrial plant space was also simulated. Repeated field evaluations will enable us to achieve technical disruptive innovation and realize social disruptive innovation that will change the disaster prevention paradigm, as well as industrial disruptive innovation, creating various outdoor services using robotics. Cyber rescue canines aim to dramatically improve a rescue dog's ability to find people in rubble piles. We are developing cyber-enhanced suits with IT functions for dogs. The dog carries out its search, relying on the scent of victims emitted through gaps in the wreckage, and informs the handler by barking when it has found someone. But if the dog gets far away, it is difficult to tell where the barking is coming from. It may even be barking because it found food. The cyber-enhanced suit is equipped with a mini video camera, inertial measurement units or IMUs, and a GPS. The IMUs track the dog's movement using gyroscopes and accelerometers. Even when a GPS signal is lost, like inside buildings and under trees, the dog's location is tracked accurately using the characteristic motions of the dog's body when it runs and walks. The dog's barking prompts searching a hole where someone could be trapped. Images from the dog cam are recorded and transmitted, showing what the dog is barking at and the surroundings. Someone is found in a sewer pipe. If a dog has to go deep into a wooded area or other places to search, such visual information is vital since rescuers are unable to reach the location easily. The victim has been safely rescued. A thin Serpentine robot called the Active Scope Camera is capable of looking for survivors in the debris of collapsed houses. The robot is designed to worm into narrow spaces in the rubble, find victims quickly, and investigate surrounding conditions. A flexible 10-meter cable equipped with ciliary vibration drive mechanism actuators can crawl its way through small gaps using a distributed drive principle, reaching deep into piles of rubble. Camera and sensors at the tip, the robot investigates inside the pile of rubble. Inserting the active scope camera from the roof, the robot searches the house interior while filming with the camera at the tip, checking house conditions. Carefully operated remotely, the robot looks for people. The building interior is in shambles. The robot must advance through cracks only a few centimeters wide and traverse large gaps, so improving motion performance is very important. To find victims, sounds from the rubble provide significant clues. However, sounds like background noise and those made by robot movement can pose a problem. Sounds from the microphone are incomprehensible. So noise is removed in real time using technologies to extract sounds and enhance them. There! The subdued voice is more comprehensible. enabling the robot to find the person while moving. The robot finds the person stuck between upturned furniture. In order to speak with a person being rescued, an offline enhancement technology is useful for filtering the voice further. But it takes time to process signals, requiring some tens of seconds to hear the voice. This is not ideal during the search. This is how robots can find a victim trapped in a collapsed house and investigate the situation. The Mini Surveyor, an aerial robot, has been improved, enabling flight stability in adverse conditions such as strong wind and rain, and in confined spaces. On the day of evaluation in the field, the wind was so strong that it blew down the chairs for the audience. Large fans were added to create an even stronger wind and more complex airflow. Despite the strong wind, the Mini Surveyor took off smoothly and proceeded with autonomous flight. Even at the entrance of a container, where the airflow changed drastically, the flight was steady. For autonomous flights, self-localization is the key. Inside the container, the robot measures and estimates its location against a map using three-dimensional SLAM technology with the help of laser sensors instead of GPS. At the time of a disaster, it is imperative to be able to fly seamlessly in and out of structures like this, regardless of environmental conditions. It is also important to be able to fly smoothly through heavy rain. A shower head is installed in the container to create the same effect as heavy rainfall of approximately 100 millimeters per hour. Even in such severe conditions, the Mini Surveyor is able to hover with good stability. The robot can also land in a water tank. Taking off and landing on the sea or a river are important for maritime rescue operations. As shown here, technologies that enable flight under severe weather conditions are being developed. Legged robots are designed to perform dangerous jobs for humans, like industrial plant inspections. This robot is capable of tasks such as climbing ladders, which has been difficult for legged robots to date. The robot moves its legs alternatively to climb the ladder, while supporting itself at 2 points at the same time. It can go up and down the ladder 12 times faster than previously possible. To achieve this, a body balancing technology controls the force and moment generated by the legs. Such a technology is required for stability if the robot receives an unexpected jolt. We believe a technology to withstand impact when the robot unexpectedly hits an obstacle or slips on the ladder can be developed. This robot is capable of performing work on ladders. On this occasion, the simple task of lighting the Olympic cauldron was demonstrated. The 4 legs have the same strong structure, which enables it to perform both power tasks and precise jobs. In the future, our goal is for it to move on rubble using all 4 legs, climb vertical ladders and stairs, and carry out heavy drilling work and non-destructive testing. Thick serpentine robots are designed to move in narrow and tight places, such as pipes in industrial plants and infrastructure, to conduct inspections. Sidewinding like a snake and lateral rolling take advantage of multiple degrees of freedom. A notable feature is the ability to perform a wide variety of movements. Furthermore, it can also move using a spiral twisting motion, which is lateral rolling carried out in a spiral shape. Spiral twisting movement is effective when moving forward inside pipes. The robot shifts and tumbles by stretching its body along the wall. In this way, it can negotiate change in the diameter of the pipes or maneuver through piles of sludge. It can also move by twisting itself around the outside of pipes. It gains a grip by constricting the pipe as if hugging it. There are many things that can become obstacles for the robot to move, including piping elbows, joint flanges, and valves that open and close the flow. The key is how to negotiate them successfully. We are hoping that robots will be able to inspect every corner of an industrial plant in the future. As shown here, the ImPACT Tough Robotics Challenge is developing robotic technologies that can perform in extreme environments such as disaster sites. These technologies will improve emergency responses to, recovery from, and prevention of disasters. More effective, safer, faster inspections. Safe and secure daily life is our goal. For the future of humanity, ImPACT.